Thank you all for having the time to join today. Today we'll be having a presentation from Moritz Fuller, and he will be talking about chain fusion, which is like talking about cross-chain interoperability, which would be powered by ICP. And yeah, just a quick note from us for all of you who are new here. We are a student initiative at the RWTH in Aachen. And without further ado, I give you, Moritz, the microphone. And after that, we will be answering some questions and have a quick conversation about that. Thank you very much.
Yeah, thanks for having me. First of all, as I already mentioned, my name is Moritz. I'm a senior developer relations engineer at DFINITY. So I'm kind of like the proxy between the DFINITY Foundation, building the Internet Computer Protocol, and developers building on top of the Internet Computer Protocol. So I'm trying to make sure that the developer experience is nice. I'm trying to educate developers through, for example, presentations like this one, or workshops, or code examples, guides, and so on and so on. And another part of my role is that I'm part of the grants committee. So I review applications of potential grantees, and also kind of like give them guidance along the process. And yeah, as we touched upon already, I want to talk about chain fusion today, which is a very unique set of technologies that the Internet Computer offers. And today in particular, I want to talk about the Chain Fusion Bitcoin edition. And that means that I want to focus on how you as a developer can leverage the Internet Computer to build smart contracts that are able to interact with the Bitcoin network, and how smart contracts on the Internet Computer are able to natively hold Bitcoin and other assets that are controlled through ECDSA key pairs or signatures. And if you want to have access to the slides, because throughout the slides there are actually a lot of QR codes, and the QR codes lead to further reading materials. So I put like this one slide here in the beginning that you can scan to get to the slides. You can open them in your browser basically. And then within the slide deck, you could just click on the QR code, and that prevents you from having to have your phone out for the next hour trying to scan those tiny QR codes on the slides. So I give you maybe 5 to 10 seconds to scan this code, and then you have all the info even after the presentation, and you can go through the deck as a sort of like a reference guide. Okay. For those of you that are not yet familiar with the Internet Computer, the chain fusion topic is actually a little bit advanced. So at the end of the presentation, there's like an overview of QR codes, and one of them is zero to depth, demystifying the Internet Computer. So if throughout the presentation there are a lot of question marks, first of all, I can answer some of the questions at the end of the presentation. But second of all, you can also watch this video series, and that's quite helpful because it gives you like a broad overview of what the Internet Computer is, how it's built, and so on and so on. But in one sentence, the Internet Computer is a decentralized and permissionless cloud built on blockchain technology. And before we start with chain fusion, it's helpful to kind of like have an understanding of the topology or the architecture of the Internet Computer. So let's just get that out of the way first. So let me see if you can see my, yeah, that should work. So at the bottom of this stack, there are data centers. So independent data centers. So not like a cloud like AWS or Google or whatever. Those are really separate, kind of like independent companies that are spread across the globe, and they provide data centers. So they provide a space where people can basically install their servers, their hardware. And the ICP topology begins with data centers. So they're at the core of everything that comes above. And within those data centers, there are node providers that run nodes. Those are the gray rectangles here. And nodes, again, form subnets. Those are the things up here. And every node can only be part of a single subnet. As an explanation, a subnet is basically a small independent blockchain, so to say. So it's a replicated state machine. And that means that every node within a single subnet performs the same computation on the same state. And as we can see here, the internet computer actually consists of many individual subnets that are all run in parallel, and it can actually, of course, all seamlessly communicate with each other. And that in turn means that smart contracts deployed on one subnet can seamlessly and transparently, from the point of view of a developer, transparently interact with each other. And this is actually the feature that allows the internet computer to scale horizontally. So if the internet computer were to need more computation or more storage or more throughput, it would just add new nodes to the network, and with those nodes create or form a new subnet, and therefore then have new capacity and new storage available. The next thing I want to talk about, now that we have like the topology out of the way, are canisters. So canisters is what we call smart contracts, just a different term basically for the same thing. And they are probably an evolution of smart contracts as you might know them from Ethereum or other so-called Gen 2 layer ones. And as a mental model, it's a lot easier to think about them as decentralized servers than as traditional smart contracts. And that is because they have some pretty unique and powerful features that are obviously made available through the platform, and that is through the Internet Computer Protocol. And today, I quickly want to just highlight the ones that we need for the presentation. And if you want to know more about the others, again, I would advise you to watch the ICP Demystified playlist on YouTube that is linked at the end. And the ones that are of importance to us today are first, the third one in the top row, so this one basically, and that is that a smart contract or a canister on the internet computer can actually call into Web2 services, like for example, the API from an exchange rate provider, or it can call into Ethereum RPC nodes, and yeah, basically any Web2 service that offers HTTP functionality using a feature that's called HTTP outcalls. And usually, if you wanted to achieve something like that, you would need to have an Oracle service like Chainlink, for example, and you would need to pay for that. And also probably you wouldn't be able to kind of like interact with the Web2, but you more likely would be able to retrieve information through some sort of predefined process or maybe pipeline that you need to set up. So it's a bit inflexible, I would say. Then the second feature that's very important today, as the name probably already suggests, are chain key signatures. So thanks to chain key signatures, canisters have control over unique ECDSA, or also since 2 weeks ago, Schnorr key pairs, and they can securely request signatures with the corresponding private key to be computed. And as I mentioned in the beginning, this enables canisters on the internet computer to natively hold Bitcoin, Solana, or Ethereum, or any other token from any other chain that either supports ECDSA signatures or Schnorr signatures. And another really nice feature is the fact that canisters have access to a very big amount of data, or access to a lot of storage, so they can store a lot of data. So currently, a single smart contract or a single canister can store almost 400 gigabytes of data, with plans to enable terabytes in the future. And here again, it's not that, like for example, with IPFS, that you can just like store basically immutable data. But the data is actually mutable, so you can update it, you can delete it, you can create new entries, and so on and so on. So it's very flexible, it's very cheap, it only costs you $5 per gigabyte per year, Whereas on Ethereum, you would, it's a one-time fee, but still you would need to pay roughly, the last time I checked, at least $80 million if you wanted to store a single gigabyte of data on chain. Okay. Yeah, maybe when you joined the meeting or when you saw what's on the agenda today, you thought like, Chain Fusion, what's that? And the truth is that Chain Fusion is kind of not really describing a single thing, but it's more like a broad term. So it's like an umbrella word that we use to describe many things that all have the same goal, and it is to fuse the internet computer together with other blockchains. And with Chain Fusion, in general, the idea is to be able to leverage the properties of multiple chains within a single dApp. So what we want to do is we want to bring the strength of the internet computer to smart contracts on other chains and also vice versa. And as I mentioned, supported chains, Bitcoin, Ethereum, most EVMs or EVM-based layer 2s, Solana, Cosmos, you name it. And that is again because those chains support either ECDSA or Schnorr signatures. And what we are focusing on today are the entries here that are circled in red. So we're going to talk about CK ECDSA, so chain key ECDSA signatures, chain key Schnorr signatures, and also the Bitcoin adapters that enable the Bitcoin integration, and then about chain key tokens. And in this particular case, we're going to talk about CK BTC. I quickly have to rearrange my monitors because they are a bit messed up. Okay. All right. So as I said, we focus on the Bitcoin direct integration today. But if you are interested in Chain Fusion in general, so basically interested in the EVM kind of side of things, then you can again scan the 2 QR codes in the top right corner. They will lead you to further reading material. And in general, what we need, or how this works on a high level, is that there are usually always 2 key building blocks involved here. And the first one is that we need a way to be able to securely read from the target chain and also write to the target chain that we're interested in. And we also need to be able to sign transactions for the other chains that we're interested in. So for securely reading from and writing to, we can, for Bitcoin at least, use the Bitcoin direct integration. This is what we are talking about today. And in the case of EVM chains or Ethereum, we can leverage that through HTTP outcalls to multiple RPC providers through the EVM RPC canister. This is kind of like a helper canister, but we're not diving into that. But this is explained in the playlist that's linked. And then for signing transactions for the other chains, we are using threshold ECDSA or threshold Schnorr signatures. And as I mentioned, if you have either ECDSA or Schnorr signatures, you can basically support all of the relevant layer 1 blockchains out there. And then, of course, what you also need is your canister that leverages those 2 key building blocks to build a dApp that makes use of this technology in a way that it makes sense. So what actually is the direct Bitcoin integration? I gave some hints already, but in one sentence, the Bitcoin integration allows canisters on the internet computer to receive, to hold, and to send Bitcoin, and all of that directly with transactions on the Bitcoin network. And to understand why this is special, or I would even say groundbreaking, we can take a look at how things used to work before this kind of technology was available. And actually also how things still work today in most of the cases, I would say. So if you think about it, right, how are assets from other chains usually made available on a target chain? This is basically what we are going to take a look at it within the next maybe 5 minutes. And a good example for such a use case, as we are talking about Bitcoin, is wrapped Bitcoin on Ethereum, so WBTC. You probably heard that recently. It has been criticized a little bit, I think, due to the fact that they changed their custodians a little bit. Not entirely sure, but yeah, it recently was at least in my X bubble for a couple of days. So yeah, what's the scenario if you want to use WebBTC on Ethereum? That's basically Bitcoin made available on Ethereum. Sounds like magic, right? But the reality is the graphic that you see on this slide. So when you use WebBTC, you're actually trusting two groups of people. The first group of people are the custodians. They hold the assets, in that case, Bitcoin. And the other groups are the merchants, and they are the only ones that are allowed to mint or to burn WebBTC on Ethereum. And even though I said custodians, on the slide is actually spelled correctly, this might be a bit outdated. I probably need to update the slide now that I see it. But pre the recent changes, it was a single custodian, so a single company that held all the Bitcoin in the system, and that company was BitGo, which is obviously also the creator of WebBTC, or the project behind WebBTC. So if you want to mint wrap Bitcoin and therefore bridge Bitcoin from the Bitcoin network to Ethereum, a merchant has to send Bitcoin to the custodian, which then upon receival mints the same amount of wrap BTC back to the merchant. So if a user, an end user, wants to bridge their Bitcoin to wrap BTC, they have to actually go through KYC and AML with the merchant. And after they did that, they then send the merchant the Bitcoin, and then they wait until they receive the wrap BTC back. And the other way around, if you want to go back from wrap BTC to BTC, you again have to send the wrap BTC to the merchant together with KYC and AML, and then wait to receive back the Bitcoin. And in the WebBTC white paper, maybe they updated it, but back then when I first created this presentation, they actually stated that you have to kind of like trust the custodian, obviously, because that's why it's called a custodian, not to run away with your funds and not to get hacked, and also to honor the one-to-one backing of WebBTC with BTC. Because I mean, the idea behind WebBTC is that you can always go back from WebBTC to BTC, and that the value of one WebBTC is basically always backed with a single Bitcoin, right? Because otherwise you could basically print money out of thin air. People on Ethereum assume that one WebBTC is worth one Bitcoin, but you do not, on the other end of this bridge, basically as a custody or as a custodian, you do not hold the Bitcoin that are associated with the WebBTC, then you basically have like a deep hack. Yeah, but what they also say to minimize the trust is that the custodians, they cannot mint tokens on their own, but they need the initiation of a merchant to do so. I would say it's fairly easy if you wanted to find a merchant to collude with, to kind of like print money out of thin air if they wanted to. So again, this is basically, you need trust into the merchants and the custodian. If you do not have that, then WebBTC is definitely not for you. What they also state in the white paper is that the framework that they set up minimizes trust, as the credibility of the institutions involved is at stake. For me personally, not really an argument, because we've seen even credible institutions being hacked, or maybe some of their employees going rogue or whatever. So yeah, when there's money involved, I'd generally try to reduce trust assumptions as much as possible. And yeah, in general, what you call this kind of schema here, or this kind of like setup here, is a trusted bridge. So a trusted bridge depends on a central entity for operation. And as we saw, it has trust assumptions with respect to the custody of the funds and also the security of the bridge. And users need to rely on the bridge operator's reputation, and they also need to give up the control of their assets to the custodian. So not really ideal. But luckily, with the Bitcoin direct integration with Chain Fusion, this changed. So over the next couple of slides, we're going to take a look at the direct Bitcoin integration that the Internet Computer provides. So what do we mean when we say direct Bitcoin integration? In our context, direct means that there are no trust assumptions required. Other, of course, than the correct functioning of the Bitcoin network and the correct functioning of the Internet Computer. So in other words, there are no additional parties required, such as, for example, in the previous example, bridges or any other types of intermediary. And through this, you have a much cleaner and more secure integration. So in essence, the difference between existing solutions and the Bitcoin direct integration is that in our case, the actual funds, so the actual Bitcoin, they are held by a smart contract directly, which is also issuing the tokens. So this is basically what I'm saying here is basically describing CKBTC, which we are going to see at the end of the presentation. Whereas with solutions like BTC, there's always some level of trust that you need to be willing to give, and always some risk of the custodians of the assets being hacked or turning rogue or whatever. And now you might be wondering, okay, I can hold Bitcoin directly in a smart contract without a custodian, without a bridge, without any additional trust assumptions, but why would I need that? Like, why is this important? And I mean, the first obvious use case is that you can use the Internet Computer as a Bitcoin layer 2, and through the Bitcoin direct integration, you have programmable Bitcoin, right? Because Bitcoin itself doesn't really have smart contract functionality, and to kind of like unlock the potential and the value locked in Bitcoin, there's currently kind of like a race who's going to be the Bitcoin L2. And we had Threshold ECDSA and the Bitcoin direct integration for over a year now, so I think we're pretty well positioned to play an important role in this space. So yeah, that's one good use case. What you can also have is on-chain Bitcoin wallet. So you can basically have a smart contract or a canister wallet that holds Bitcoin on your behalf, and you could authenticate to this smart contract wallet, not using a seed phrase or a private public key pair that you somehow have to keep safe, but you could, for example, use WebAuthn and passkeys or whatever other authentication scheme that you could think of to authenticate to this Bitcoin wallet. Then through more through CKBTC that we're going to talk about later, you can send Satoshis, for example, via a chat message in a SocialFi application. You can, of course, because Bitcoin are available on the Internet Computer, trade Bitcoin. You can also trade other meta assets like runes or BRC20 tokens on the Internet Computer and a DEX. You could, for example, build a lending market that uses ordinals as collateral. Then CKBTC that I mentioned a couple of times already. And for example, also a smart contract managed BRC20 index fund. I mean, all of those things are possible. And some of those are actually being built. I think actually a majority of what I mentioned now is being built by some projects in our ecosystem. Okay, so before we dive deeper into the inner workings of the Bitcoin direct integration, I quickly want to explain the concept of UTXOs. So as a simple example here, Alice on the left-hand side wants to send 400K Satoshis over to Bob. And to do this, she has to consume 2 UTXOs, or unspent transaction units, that together add up to the 400k Satoshis that she wants to send over to Bob. So what Alice does is that she creates a transaction, so the thing here, with the 2 UTXOs that are being consumed as an input, and the new UTXO that after the transaction is included in the block and mined now belongs to Bob and is basically the output of the transaction. And as you can see, the inputs to Alice's current transaction are outputs from previous transactions. So if you want to create a transaction on the Bitcoin network, you have to spend UTXOs. And obviously, you can only spend UTXOs that you own. So every UTXO has a public key associated with it. And you can prove your ownership. So basically, you can prove that you have the authority or the right to transfer or to spend those UTXOs by creating a signature that's associated with the public key attached to the UTXO. And this is indicated here on the slides by this blue ribbon. So in this case, Alice created a signature on the transaction input, so on the UTXO, and that signature can be verified with the private key that is associated with the UTXO, with the public key that's associated with the UTXO. What happens next is that the transaction gets included in the block together with many other transactions, and the blocks are then chained up and form what's called a blockchain. So I guess most of you are familiar with that, but maybe the UTXO kind of like mechanic wasn't that clear yet. Okay, so we will need this in a bit. So with the UTXO stuff out of the way, as we said in the beginning, there are 2 building blocks needed to enable chain fusion. So on one hand, we need to be able to read from and write to the chain that we want to integrate with. And on the other hand, if we want to transfer value, of course, we need some signing capabilities, right? We need to be able to sign a transaction that is then written, so to say, to the blockchain that we want to integrate with. And for reading and writing, the Bitcoin API can be used. This is basically what the Bitcoin API is enabled by the protocol level integration of the internet computer with the Bitcoin network. And the integration allows canisters on the internet computer to fetch Bitcoin balances, block headers, UTXOs, and also allows them to send transactions to the Bitcoin network. And this is going to be covered in the next 2-3 slides. And then for signing, we have the threshold ECDSA and threshold Schnorr API that we developed. And this is basically not only the signing, but it's actually a protocol suite, the chain key protocol suite, or chain key signatures protocol suite. And this protocol suite includes protocol not only for the signing, but also for example, key generation, public key retrieval, and a couple of other things. So it was a pretty big R&D endeavor, and of course also a lot of engineering hours spent to implement this securely and in a decentralized way. So let's start with the Bitcoin API. So let's start with the thing that allows us to read from and write to the Bitcoin blockchain. And on this slide, I quickly want to walk you through the functionality that the Bitcoin API offers. So the things with the gray background here, they're actually function calls that are exposed by the protocol that you can, if you're developing a smart contract, just call into. And of course, you need to provide some arguments and you receive a response. But yeah, it's pretty straightforward. It's like calling an API, obviously. That's why it's called Bitcoin API. All right, so the first thing is that through this Bitcoin API, as I mentioned, canisters can run queries against the full Bitcoin UTXO set. And this allows canisters to know about the held UTXOs and thus also the balances of any Bitcoin address. So Bitcoin get UTXOs, you provide a Bitcoin address, and it gives you the UTXOs for this Bitcoin address. And with the balance, instead of getting the UTXO, you get like the amount of Satoshis that are the sum of all UTXOs held by a certain address. The next function is Bitcoin send transaction, and this allows canisters to send signed transactions to the Bitcoin network, and when they do, that's a pretty cool thing. The internal computer nodes. So if you remember the architecture that we covered in the beginning, every node in the Bitcoin activated subnet directly transmits the Bitcoin transaction to other Bitcoin network nodes. So every node in this Bitcoin activated subnet is connected to, I think, 100 other peers in the Bitcoin network. And when you want to send from your canister smart contract a transaction to the Bitcoin network, it gets basically pushed down to the nodes that are part of the subnet, and every single one of these nodes sends your transaction out to roughly 100 different actually peers in the Bitcoin network. So you have a very broad and nice distribution of your transaction. And again, no intermediary that might censor you, right? Because you're not depending on a single node or a single entity that forwards your transaction to the Bitcoin network. No, every node in the subnet is basically transmitting your transaction to the Bitcoin network. So that's pretty cool. Then we have the Bitcoin get current fee percentiles method. Sounds long and complicated, but it's actually very simple. It gives you the current transaction fees for transactions. So that's obviously helpful if you want to assemble a transaction. It's good to know how much it costs, so you can dynamically adjust the fees. And then, last but not least, canisters can also request block headers, and that's useful in some situations where the canister can basically fetch a raw transaction with a Merkle proof from an untrusted source and then verify that the transactions or the transaction is actually part of the Bitcoin blockchain. So that's also neat. And then let's go a level deeper and look how this API is actually enabled. So now we kind of like know what programmers use and what functionality is there, but you might be wondering, okay, but how is this actually enabled? And this is what we see on this slide. So the components that enable the Bitcoin API or the Bitcoin direct integration are actually two. The first one is the Bitcoin adapter. This is in the bottom right corner here. And the second one is the Bitcoin canister up here. And let's start with the Bitcoin canister. So the Bitcoin canister lives on the so-called Bitcoin activated subnet and is actually just a normal canister as any other canister. It's controlled a little bit differently. It's controlled through an on-chain DAO that's called the NNS, or Network Nervous System. But apart from that, it's basically just a canister like other canisters on the network. And this canister, you cannot really call directly. You call it through the so-called management canister, which is a facade. It's not really a canister. It doesn't really exist, but it exposes some of the system functionality, and that is, for example, the Bitcoin API or the threshold signing methods. But for you as a developer, it's basically like calling any other smart contract that is deployed on your computer, so you don't really see a difference. And what this Bitcoin canister does is that it holds the on-chain Bitcoin-related state, and that is the full UTXO set, outgoing transactions, and also the most recent Bitcoin blocks to allow for fork resolution if necessary. And the Bitcoin editor down here connects to the Bitcoin network. much like a regular Bitcoin node would do. It's kind of like a node stripped away or stripped of everything that's not related to getting the latest blocks and ingesting them into the Internet Computer Network. But it does connect to other Bitcoin nodes in the Bitcoin network, and to them, the Bitcoin adapter is like any other regular node, so they don't really see the difference. And through the setup here, the Internet Computer can actually obtain Bitcoin blocks from the Bitcoin blockchain or from the Bitcoin network and process the transactions that are contained within those blocks. Was this one too far? No. Okay. Yeah, now you might ask yourself from the previous slide or from the first slide when I talked a bit about the Bitcoin API and I said that canisters have access to the full UTXO set on chain. You might ask yourself how this works. So it works by the on-chain UTXO set held by the Bitcoin canister being managed by both the Bitcoin adapter and the Bitcoin canister. And those two components, they communicate through the Internet Computer's protocol stack. And this process of communication starts with the Bitcoin canister requesting successor blocks to the latest block it received from the Bitcoin adapter. The Bitcoin adapter on each replica, so basically on every node in the subnet, then obtains the latest block from the Bitcoin network. And then next, the block making replica for this round provides the requested block to the Bitcoin canister through consensus. And then once the Bitcoin canister receives the block, the Bitcoin block, it extracts the UTXOs from the transactions contained in the blocks and then updates the UTXO set that it maintains in replicated state. And this is actually the mechanism that allows the Bitcoin canister to maintain the full Bitcoin UTXO set on chain. And the same mechanism is also used to get the block headers into the Bitcoin canister. And for the get recent fee percentile method, the last, I think, 10,000 transactions are analyzed, and you basically receive the different fee percentiles if you call it endpoint. And you can then make a decision how you want to set your own transaction fee to increase the chance that the fee was set high enough and that the block is included, the transaction is included in the block. And yeah, to enable this, basically to enable that the canister is able to hold the full UTXO set on chain, we need this storage capabilities that we talked about in the beginning on this overview slide of the capabilities. Because I think the UTXO set has, I think, roughly 5 gigabytes or something. But with indexing, so that the get UTXO endpoint on the Bitcoin API and get, or the Bitcoin balance, I don't know what was it called. Get balance API method to enable, then you need indexing, right? Because otherwise, it takes too long, or the computational overhead is too big. And like with indexing together, it consumes the UTXO set. It consumes roughly 100 gigabytes of on-chain storage. So that's pretty big. And I would say it's also pretty impossible to build something like that on other layer ones, either because it's technically not possible, because the smart contracts that they offer maybe only have, I don't know, maybe 1 or 2 megabytes of storage, or if it were possible theoretically, it's practically not possible because the costs are so high, right? So you don't want to pay 80 million per gigabyte. But the Internet Computer has been designed to enable such use cases, so there it works. Okay, so what we described now basically enables the Bitcoin get UTXOs because of the UTXO set in the canister, then the Bitcoin get balance because we have the indexing that allows us to kind of like get all the UTXOs for an address and then just return back the total amount of Bitcoin that are held by this address. And the missing one, we also talked about the headers and the fees, but the missing one is now how can I actually send a Bitcoin transaction? And if you build a Canister smart contract and that Canister wants to send a Bitcoin transaction, the Bitcoin transaction is actually submitted to the Bitcoin Canister first, where it's queued. So basically, this is depicted here. And what happens then is that every subnet round, the Bitcoin Canister, or the Bitcoin adapter actually, on every replica obtains the pending transactions from the Bitcoin Canister and queues them for being submitted to the Bitcoin network. And as I mentioned, this gives you this nice broad distribution. So yeah, that's a pretty good way of distributing a transaction in the network and increasing the chances of it being included in the block if you set a high enough fee. All right. So this covered the first building block. So the left-hand side, read from and write to your target chain, in that case, Bitcoin. Next, I want to talk about the other key building block, so the right-hand side of the slide, and that was how can we securely sign transactions for the Bitcoin network? And this is actually enabled by the chain key signatures feature that kind of like mentioned already. And that consists of a threshold signature scheme where the private key is shared across the nodes of a subnet. And the chain key signatures actually come in two flavors. So we have threshold ECDSA, and now since I think a week or two ago, we also have threshold Schnorr signatures. And what I mean by shared across the replicas of a subnet is that the secret key, so the ECDSA, for example, secret key, is basically split up into many secret shares. And each one of those secret shares is stored on a different node of the threshold signing enabled subnet. And of course, the subnet is a so-called high replication factor subnet. So that means that there are more nodes in the subnet than in usual regular application subnets. And if a smart contract, or if the network or the subnet in general wants to sign a message, all the nodes in the subnet must coordinate to generate that signature in a distributed fashion. And here at least 1/3 of the nodes are required to jointly create a signature using their respective key shares. And through this threshold signing capability, or threshold ECDSA capability, canisters on the Internet computer have control over a unique ECDSA and Schnorr key pair, and they can also request signatures with the corresponding private key to be computed. And actually, from this key pair that a canister has access to, an unlimited number of keys can be derived. So that means that your canister doesn't only have a single Bitcoin address derived from the public key, but it actually has access to unlimited public keys and therefore also unlimited Bitcoin addresses. And that is actually quite helpful, as we'll see later with the CKBDC Minter. And I want to highlight this again because it's important to remember that the private key, the private threshold ECDSA or secret shared threshold ECDSA key never exists in reconstructed form, but only in the secret shared form. So even when you're assigning the messages, there's never a situation where the private key is somewhere in plain text. That's not how those threshold signing protocols work. And through those ECDSA or Schnorr threshold signatures, your canisters or your smart contracts on the Internet computer can natively hold Bitcoin, Solana, or Ethereum because they all support ECDSA or Schnorr signatures. So there's again an API for this kind of functionality, for the signing functionality, and then there's one API for ECDSA signatures, and there's another API for Schnorr signatures. I quickly want to go over this. I'm not going to cover the Schnorr one because it's actually almost the same. But so if you want to get the ECDSA public key for a canister and for a certain canister and for a derivation path, which is basically how you obtain those unlimited other public keys through the derivation path. This is what the interface looks like. So as a programmer, if you build your canister smart contract and you want to use ECDSA and you want to retrieve the ECDSA public key for your own canister, for another canister, this is the method that you need to call. So you provide the canister ID that you want to retrieve the public key for. If you don't provide it, it's assumed that the canister that you are calling one from is the one that you want to get the key for. You provide a derivation path, which is basically, kind of like I think derivation path is already the best word for it. So it describes at what path you want to derive a public key, and it gives you access to this derived public keys from a single canister at the root of the tree. And then you can also provide a key ID. So there's not only a single threshold ECDSA key, but there can be many of them or a number of them. So you can spin up a threshold ECDSA subnet or a signing subnet, what we call them. And because there could be many of them, there could be also many keys, and therefore you need to provide the curve and the name of the key that you want to retrieve the public key from. And on the other hand, if you want to sign a message with ECDSA, for example, if you created within your canister smart contract, you created an Ethereum transaction that transfers, let's say, I don't know, 1 Ether from the address that your canister smart contract controls to a different address. Of course, you need to sign that transaction with a key that belongs or that controls the address. And here, what you have to provide is the hash of the message as an argument, then again, the derivation path, and again, a key ID. And for Schnorr signatures, is basically the same thing. So again, on the left-hand side, you can see how you would retrieve a public key, and on the right-hand side, you will see how you can create a signature. So as a developer, how would you leverage this Bitcoin integration in theory? Let's take a look at the full flow of sending a Bitcoin transaction on the Bitcoin network from a canister. And in this case, the canister holds obviously the funds that we want to send. So first, our canister smart contract would have code that would get the UTXOs that are under its control, because we need to create a signature on every UTXO. So we need to know what the UTXOs are. And then because we have to, on Bitcoin, pay a transaction fee, we also want to know what the recent transaction fees were to set it to a good value to make sure that it's included and in a block and that it's mined. And therefore we call this Bitcoin current fee percentile. So now we have the UTXOs that we want to transfer to a different address that belong to our address at the moment, or to the canister's address more precisely. And we know the current Bitcoin fees, so we can set appropriate fees for our transaction. So next, what we do is that we actually create a Bitcoin transaction, including the UTXOs that we retrieved from the Bitcoin canister. And now creating the transaction is not enough, right? We have to prove our ownership of every UTXO that we want to use as an input to the transaction. So now we call the sign with ECDSA or the sign with Schnorr functions or API methods that we saw earlier to create a signature on every UTXO that we want to use as an input to our transaction. So once we have that, we can now take the signed transaction and we can send it to the Bitcoin network using the Bitcoin send transaction API call through the Bitcoin canister. And the Bitcoin canister, as we saw, is now relaying the signed transaction to the Bitcoin network through the nodes that are part of the Bitcoin subnet or the Bitcoin activated subnet. And that's basically it. So this is how a canister is able to control Bitcoin, hold and send or control Bitcoin on the Bitcoin network without any intermediaries, without any bridges, and without any additional trust assumptions. But because this management canisters API that we saw, so basically the Bitcoin API and also the threshold signature API, because those two are a bit low level, and also because if you make transactions on the Bitcoin network, they are still expensive and slow. Even if you're doing it from a canister, it doesn't really change anything, right? Because the Bitcoin network is still the one processing the transaction. So because of those two reasons, most projects, if they want to use just let's say the value that's locked in Bitcoin, will most likely use chain key Bitcoin, so chain key BTC, if they are built on the computer. So as an explanation, CKBTC is a synthetic Bitcoin twin token on the internet computer that has, for example, a much stronger underlying trust assumption or trust model than existing wrapped or bridge BTC versions. And that is because of its decentralized architecture that we are exploring now, and the fact that it's built on top of chain fusion with the Bitcoin direct integration instead of, for example, a centralized bridge, as it is the case with wrapped BTC. And as I said, it's easier to integrate. So CKBTC is easier to integrate because you're not using those low-level Bitcoin APIs, but you can, in your dApp that you're building, simply access the CKBTC ledger like any other ICRC1 ledger on the internet computer. So ICRC1 is basically the equivalent of ERC20. So it's just a token contract, so to say, that you integrate with, and where you make transfers and where you make approvals and things like those. So yeah, it's a lot easier to integrate than trying to integrate Bitcoin transactions directly, and it also offers, of course, a lot of a better user experience, because if you transfer CKBTC, that the CKBTC ledger lives on the internet computer, and therefore you also have the low finality time of the internet computer, which is 1 to 2 seconds most of the time, and also the transfer costs you a fraction of the cost, right? I think it's currently roughly a cent or a little bit less than a cent. I think the fixed price is 10 satoshis, but I'm not sure how much currently 10 satoshis are. I think it's less than a cent. While on Bitcoin, if you were to make a native Bitcoin transfer on the Bitcoin network, that would definitely cost more than 10 satoshis. So if you use this kind of scheme, the only transfers that you have to do on the Bitcoin network are basically the settlement transfers. So if you go from Bitcoin to CKBTC, you need a transaction on the Bitcoin network, and then also the other way around. If you want to get your Bitcoin, your native Bitcoin back, and you want to get rid of your CKBTC, this of course also has to be settled on the Bitcoin network. But in between, the majority of the transfers can be done with the lightning speed and the low cost that the internet computer offers directly on the internet computer. So in this architecture here that we see, there are a number of different components involved. So the first one up here is the CKBTC minter, and this canister holds Bitcoin or the Bitcoin on the Bitcoin network that are associated with this entire dApp. So basically the backing of CKBTC is held by this canister, and it is also responsible for minting and burning CKBTC on the CKBTC ledger accordingly. And then, yeah, we have the CKBTC ledger. So this is used on the intercomputer network to record the balances and facilitate CKBTC transactions and other things that you would expect from a ledger. Then we have the Bitcoin canister. We know that one already because we talked about it in the previous slides. And this Bitcoin canister is used by the CKBTC minter to get UTXOs and also to send transactions. And then we also have a KYT canister that we are actually in the process of getting rid of. But as of right now, I think it's still used to make sure that the CKBTC minter only has clean UTXOs and that it only interacts with clean addresses. But this will be replaced with, I think, basically an OFAC block list or blacklist or whatever it's called. And one component that's not shown here, but that we also talked about, is the management canister that provides the Bitcoin API, because this is needed for the CKBTC minter to actually sign Bitcoin transactions in case a user wants to burn their CKBTC and receive Bitcoin on the Bitcoin network. Of course, the CKBTC minter, has to create a transaction and sign that using the management canister.
All right. I'm sorry to interrupt you, but
yeah,
we are running slowly out of time. Maybe if we could
it's just
wrap up
2 more slides.
Okay.
So I think
Perfect.
roughly maybe
work.
5 minutes, if that's okay.
That's fine. Yeah, totally.
Okay, awesome. Yeah, and to wrap things up, I quickly want to walk you through the flow of converting Bitcoin into CKBTC on the internet computer, which is basically the equivalent of what RepBTC does, but in our case, in a decentralized way. And we start by querying the CKBTC minter for a Bitcoin address that is reserved for us, basically for the caller of this endpoint on the Bitcoin network. So the CKBTC minter canister gives every user that interacts with it a unique address on the Bitcoin network that is only reserved for this single user that interacts with it. And it does so by kind of like deriving this Bitcoin address using our principal, which is basically our address, and using this as a derivation path when calling the ECDSA public key endpoint provided by the management canister. And I mean, it is unique to us, to the person interacting with the CKBTC minter, but of course the CKBTC minter controls it, right? Because the CKBTC minter is the only one that has authority to request signatures corresponding to the public key. It is basically kind of like an escrow or network custodied kind of architecture. So now we have a deposit address on the Bitcoin network. And what we do next is, of course, we transfer our Bitcoin that we want to convert into CKBTC through that address on the Bitcoin network. So this happens here. And then once this transaction is finalized, we call the update balance function on the CKBTC minter. This is basically informing the CKBTC minter about the fact that our funds arrived and that it can now basically double check that the funds are there. And then, if so, mint us the corresponding amount of CKBTC on the CKBTC ledger on the internet computer. So what the CKBTC minter does upon you calling this update balance endpoint is that it calls the Bitcoin canister's get UTXO method. So it checks for this address that is again derived by your address, for this Bitcoin address that is derived from your principal. We call addresses principals. If there are UTXOs available that it has not yet seen. So of course it filters, because otherwise you could call this 20 times and it would mint CKBTC 20 times, but no, it basically keeps track of which UTXOs it has already seen and only mints CKBTC for the ones that it has not seen yet. And this is happening here. So if the minter makes a transfer, this is basically the equivalent of a mint. And that's it. Then you have your CKBTC. The CKBTC minter is basically escrowing or the smart contract holds the Bitcoin, and you in return receive the CKBTC. And the other way around, the flow is based on the ICRC2 standard, which is basically an approval transfer from flow. So the first step is that we have to approve the CKBTC minter on the CKBTC ledger to transfer the X amount of CKBTC tokens on our behalf. If this is done, we then call the CKBTC minter with the or on the retrieve BTC with approval endpoint. Here we can provide an amount that can be smaller than the amount that we approve for, of course. It can be bigger, but it can be smaller. And we also provide an address that we want to receive the Bitcoin on the Bitcoin network to. And then what the CKBTC minter does is, on our behalf, using the transfer from endpoint on the CKBTC ledger, it burns our CKBTC tokens, and then it's basically so it's basically putting the request that we want to have Bitcoin, and we already burned CKBTC into like a queue, and then we have on the computer we have timers, so a smart contract can call itself regularly without any off-chain infrastructure, so like a cron job basically. And using a timer, the minter then kind of like batches a number of requests. Instead of for every request creating a new transaction on the Bitcoin network, it batches requests up to 100 can be batched. And what it does is that it selects UTXOs from different addresses that it controls with a total sum of at least the sum of retrieval requests. So if people want to get 100 Bitcoin out, then it would, for example, I don't know, assemble UTXOs that are worth 101 Bitcoin, and then it would construct a transaction with the selected UTXOs as input and an output for each retrieval request. It will sign each UTXO using threshold ECDSA, and it will then send this transaction to the Bitcoin network using the Bitcoin API. And that's basically it. This is how you go the other way around. Okay, and yeah, that's it. Here are a couple of resources. So this is a collection of very helpful resources if you plan on building dApps on the internet computer. If you have questions, there's a developer forum where you can ask questions. A lot of our employees are on this forum. So basically the engineers that work on the protocol or the researchers, they're in here and happy to answer questions. This is a plug for the German ICP Hub. They have a Telegram channel. You can follow this QR code. If you are interested in the Bitcoin integration, this is documentation for that. We also have a video series about Chain Fusion. So this is worth watching if this topic was interesting to you. We also have developer grants. So we give out non-dilutive funding for developers that want to build on our platform. This is this, basically ICP demystified playlist that I mentioned earlier. And if you are an Ethereum developer, you can read this guide that gives you a bit of background about the differences and similarities between the internet computer and Ethereum. With that, thank you for having me.
Yeah, thank you very much for the presentation. I think we already have one question from the audience. Maybe we have some time to discuss this, or if it's too much, then we can also discuss through a forum. So there's who says, if we have time left, how does ICP interface with protocols on Ethereum, like facilitating an ENS domain mint with CKBTC?
Okay, where can I find this question? Or is it in the Google Doc?
It's here in the chat from this meeting, in the down right
okay,
corner.
Sorry. Yeah, okay. How does ICP on ETH like facilitating an ENS domain mint with CKBTC? Okay, I mean the first part. So how does ICP interface with protocols on Ethereum? So this is, I mean, kind of like a fundamental question. So it again boils down to the protocol needing a way to reading from and writing to Ethereum or other EVM chains, and then again needing to be able to create signatures that are supported by the other blockchain. I mean, signatures, we already covered this, right? Ethereum and Bitcoin both support ECDSA signatures, so that part is clear, I think. So if you have a EIP 1559 transaction assembled in a canister, maybe using Alloy and Rust or whatever, you need to create an ECDSA signature on it, and this you can easily do by this management canister endpoint and that I shown earlier, basically sign with ECDSA. So that part is quite straightforward. The other part, how do you read from and write to Ethereum, is a bit more interesting. I have actually some backup slides. Let me pull them up real quick. I think I have to share my screen. Or can you still see my screen? Yeah, you can still see it. Okay. So I mentioned this HTTP outcall feature earlier, right? So a canister can just call into an API that's on a server or hosted from a server, whatever. And that means that a canister can also, of course, call into an EVM RPC provider. So you can call the methods exposed by an EVM RPC provider, like Alchemy or Infura or Cloudflare or whatever. And this enables you through those HTTP outcalls to read state from the Ethereum network. And if you want to write state, you basically assemble the transaction in your canister that would, for example, make a smart contract call or whatever. And then again, you sign that using ECDSA, and then you submit the signed transaction to an EVM RPC provider, and that way you can write to EVM chains. I mean, I think there's a better overview of this. Yeah, here, for example, I mean, you have your transaction that you create in the canister. You then create a Ethereum, an ECDSA signature on it, and then you submit the signed transaction to an RPC provider. And actually, I mean, there's a convenience canister that does that kind of for you, because of course you don't want to rely on a single RPC provider, right? If you imagine you rely on only Infura, and then it turns out one day Infura got hacked, or there was an employee that served you wrong responses to the request that you sent, and that would be really, really bad. And to avoid that, what this EVM RPC canister, which is a helper canister that developers can integrate with, and what this does is that it sends the request not to a single RPC provider, but it sends it to many, or actually it's, I think, 5, and you need 3 of them to be or to have consensus. It sends it to 3 RPC providers, and then it receives the response, and then it makes sure that the response received from those 3 RPC providers that they are the same, or that they have consensus on the response, and only then it forwards the response over to the calling canister. So this is how you would integrate with Ethereum. And there were plans for a direct integration as well, and there are also some light clients running in a canister on the internet computer. But I think as of now, I think the way that I just described is probably going to be the meta for, I would say, at least a half a year or 3, or maybe a year even, until developers say, this is not good enough. We need more, and then we are probably going to roll out a direct integration for Ethereum as well. But of course, you cannot, I guess, depending on how you solve it. But if you go for this protocol level integration, then it becomes a bit infeasible for us to develop a single unique way of integrating with a chain for every relevant chain out there, because then we would need to integrate with, I don't know, 20 different chains in 20 different ways. So yeah, probably will boil down to some sort of light client solution, but not my area of expertise, unfortunately. But this is a good question for the forum. And you said facilitating a mint with CKBTC. So facilitating the mint with CKBTC will be a bit difficult because, I mean, you need to pay the transaction fee in ETH, right? So you cannot take CKBTC and tell Ethereum miners, even if it would work, tell Ethereum miners like, hey, please take the payment in CKBTC instead of ETH. So what you would need to do is you would need to swap on the internet computer the CKBTC for CKETH. And then you would need to let's call it unwrap the CKETH into native ETH, because we have CKETH, which is basically the same thing as CKBTC. So again, there's a smart contract on the internet computer that holds Ethereum on the Ethereum network natively. And of course, you can go back, so back to ETH from CKETH. And what you would do is exactly that. So you would need to convert the CKETH into ETH, and then you would have funds available to pay for the transaction fees on Ethereum. When you submit the transaction to the Ethereum network. This is how you could implement it.
Right. I hope that answers the question, Lucio. I think we have time for one more question. If there is someone interested to ask, just open your mic.
In any case, maybe some advertisement. There will be a hackathon for Chain Fusion and focusing on Bitcoin enabled for Chain Fusion. So if you're a developer, then I would encourage you to look out for that. There will be bounties. I think we are giving out like, I don't know, 15 or 20K US dollars in ICP. And with that, I mean, if there are no more questions, if there's something coming up after the presentation, feel free to join the forum. You can always ask your questions there, or you can reach out to me directly. I go by Dr. Schindler basically on all social media platforms. And also if you want to discuss grants or anything else that's on your mind, I'm there for you.
Excuse me, I think I have a question, and it's about how can users basically be able to use your services, and in what way basically? Is it something similar to Fractal Bitcoin, where we can basically be able to make applications and be able to index them in your protocol, or is it actually different?
I'm not too familiar with Fractal Bitcoin, but from a developer point of view, the internet computer is basically a general purpose compute platform. So you can deploy any logic that you can think of within a smart contract on the internet computer. And through the kind of like capabilities that I described throughout the call, you have access to UTXOs within or owned by. Yeah, go ahead.
So it works basically the same way as the BRC20, CAT20 protocols that are basically new on Bitcoin right now. The implementation is also similar to Fractal Bitcoin, but Fractal Bitcoin is considered a sidechain. While basically for Bitcoin, the use of UTXO is basically to host, for example, inscriptions, for example, pictures and tokens and other stuff like this can still be applied as an application by inscribing them, signing a transaction basically that sets the UTXO on the chain. Does your service actually work the same way, or it works differently?
I would say it works differently, because what you described, like BRC20 and ordinals and runes, they are meta protocols. So they are, at least to my knowledge, not really decentralized, and they also rely on indexers that basically extract the meta information from the Bitcoin blockchain, and on top of that give you some sort of balances or other things. So I would say it's not the same thing, but you have the possibility. For example, we have projects that deployed indexes for ordinals or for BRC20 tokens within a canister on the internet computer. And you can, because we have threshold Schnorr, you can create transactions that transfer ordinals or runes from one address to another. So that's definitely possible. I don't know if that answered the question. But,
yes, it did. Yes, it did. Thank you so much. I really appreciate it.
Okay, you're welcome.
All right. Well, thank you very much. We unfortunately don't have more time for questions, but feel free to join the links that Moritz mentioned and drop your questions below. Also, thank you very much, Moritz, for being here.